Hello, I'm Luis Serrano, and this is Serrano Academy, and this video is about group relative policy optimization. Group relative policy optimization is a wonderful way to train large language models for reasoning purposes. GRPO got introduced in this paper by DeepSeek, and as you may have seen, DeepSeek introduced a really powerful reasoning model with very few parameters. So this method is what made it work so well. And here's the idea between a reasoning model. The idea is to make it solve problems. For example, math problems, but anything that requires reasoning. So we're going to use this problem throughout the whole video. Solve for x in the equation 2x plus 4 equals 10. So the solution is x equals 3. So I'm going to give you some solutions that the computer may give, and you help me think of which one is the best one. The first one is x equals 6. The second one is x equals 3. And the third one is subtract 4 from both sides, get 2x equals 6, and then divide both sides by 2, so you get x equals 3. So how would you rank these three solutions from best to worst? Well, clearly solution 1 is the worst because it's plain wrong. Between 2 and 3, though, I would say that 2 is the so-so one because it only shows the answer, whereas solution 3 shows its work and it's fully correct. Every step is perfect. So this one's the one that wins, and what we're going to do is train a model to produce solutions like the third one. Now, how do we do that? Well, we can tell the model explicitly, hey model, don't just answer the question, give me a bunch of steps that lead to that solution. Now, in order to train a model to give an answer by showing intermediate steps, we have two main ways to do it: self-supervised learning and reinforcement learning, or GRPO. Self-supervised learning is what ChatGPT originally used to train the reasoning models. And then DeepSeek knocked it out of the park by introducing reinforcement learning, and now they use a combination of things. But let me show you self-supervised learning. Basically, we want to solve a math problem. How do you do it using supervised learning? Well, you produce a lot of data for the model to learn. And the data, you produce it by hiring a lot of really smart people. So you hire a lot of mathematicians or people who can solve these math problems, and they produce a lot of solutions. And we tell these people, hey, write the solutions using carefully written steps. And then we feed those to the model, and the model learns to write solutions the way they were given to it. It's basically supervised learning. Now, how do we do this with reinforcement learning? We make the computer play a game, basically against itself. What we do is we use the model to create a solution, and we tell it to write the solution using a bunch of steps. These steps could be completely wrong, but it doesn't matter. Its solution comes out with steps. And then we use the same model or other methods to actually check if the steps are okay one by one and if the solution is okay. Now, there's a strength that these models have. They're not so great at creating, but they're really good at understanding previous stuff. So actually, a large language model can be really good just by itself at grading problems. It may not know how to produce solutions so well, but it can grade them well. And that, used in combination with other methods, say software that can check the math or several heuristics, then we have a really strong grader. And since this grader is really strong, then it feeds information back into the original model, and the original model is able to create better and better solutions. Now, why is this method better than that one over there? Well, for instance, that one is really expensive. It's really expensive to get a lot of people to produce a lot of solutions. And also, it's limited. The model can only be as good as the top person who creates these solutions, whereas this one over here has no limit. It can really come up with reasoning methods that maybe humans haven't even come up yet. It's analogous to how we get computers to play games like chess and Go. We can record a lot of games and give them the games in a supervised learning way, or we can make the computer play against itself. And it's shown that letting the computer play against itself can produce a much better model. And actually, that's how models were able to beat the best human at chess and at Go. Okay, so that was the overview, but now let me get into the details of GRPO. As I said, we're gonna focus on that problem. Solve for x in the equation 2x plus 4 equals 10. The solution is 3. Now let's say that the model outputted some solutions with steps, because we told it to do it with several steps. And the first one is this one. As you can see, it's completely wrong. It's doing some wrong steps and then gets the wrong answer, which is x equals 4. The second one does some steps which are not great, and then actually comes up with the correct answer. So that could happen. And the third one is the perfect solution. Okay, it subtracts 4, then divides by 3, and gets x equals 3. So the question is, how are we going to grade each one of these three to tell the computer to produce more solutions like number 3 and less solutions like number 1 and also like number 2. So first, let's grade every step. Everything on the first solution is wrong. The 2 steps and the solution are all wrong. So this one gets a really bad score. Solution 2 has one step that's incorrect because multiplying both sides by 2 doesn't help. Then it has a correct step, which is subtract 8 and divide by 4 and get x equals 3. So it managed to correct its way. So it's not so bad. And then it got the right answer. So this one gets a so-so score. And then the third one is perfect. It does the correct steps and it gets the right answer. So this one gets a good score. And what's the score that they get? It's this big ugly formula over here. Now this looks very ugly, but I promise we're gonna go over every single detail of this formula and you're gonna notice that it's actually pretty simple. So when you see formulas like this, don't get scared. It's a cryptic way to convey some really nice ideas. So let's go for the easy part. That first summation, well, that's just the average over all the responses the computer gives you. The computer gives you 1,000 responses, then you just add all the scores and divide it by 1,000. What did the second one do? Well, let's say that you have an answer with 10 steps. The last one is the answer. So we simply score each step, including the answer, and then divide by 10, which is the number of steps in this case. So that's the aggregation part. What is the next one? This over here. That is the probability of a new response divided by the probability of an old response. I will get to this. Then this A over here is a score for the quality of each step of the response. Notice that the A has a hat, and the hat is because we normalize the scores. I promise I'll get into all these details. Then you may see this clip over here. Well, the clip is just a tool we use in case the numbers get too big. We don't want to throw in 1,000 there. It's like throwing a wrench in a machine. So we actually want the numbers to stay small. That's what the clip function does. And then finally, this thing over here is called the KL divergence. That just makes sure that the model doesn't deviate too much from the previous one. You want to make these changes small and gradual. The moment you start making big changes in the model, things get risky because you may fix one solution but mess up all the other ones. So that's it. That's the formula. Let's get to each detail. Let's start with the first one, average over all the responses. Well, simply all we do is if we have the problem, solve x for the equation 2x plus 4 equals 10, then if the computer produces all solutions, G of them, we simply score each one of them and then take the average of the scores. Very simple. Now the next one is the average over all the steps. Well, if a response has a lot of steps, we simply score each step and then take the average of all the scores. That O sub I there is the number of steps in a solution, including the answer. Okay, let's get to the meat of the subject, the quality of the steps. So this is this one over here. And let's forget about the hat. I'm going to tell you what AIT is first. We're going to go back to our problem. Solve 2x plus 4 equals 10 for x. Now, we're going to have, again, solution 1, solution 2, and solution 3. And let's remember that solution 1 is incorrect for the answer. And solutions 2 and 3 have the correct answer. So that's the last step of the solution. Each one has 3 steps. And as for the steps, well, they're both wrong in solution 1. For solution 2, one is wrong, one is right. And for solution 3, both are right. So we're just going to come up with some numbers. And the numbers can be, let's say, we're going to subtract 0.1 every time there's a bad step. We're going to add 0.2 every time there's a good step. And then for answers, we're going to be a little more drastic. We're going to say that a bad answer gets some score of -1 and a good answer score of +1. So we score every step in here. And then we could probably add them, but we're not going to add them. We're going to first normalize the data. What does normalize the data means? Let me give you a very, very quick recap. Let's say I have 3 numbers, 1, 4, and 10, and I want to calculate their average. Why? Because the average is the center. Now, I want my data to be centered around 0. So what I do is I subtract 5, the average from everything, and I get -4, -1, and 5. Now, this data is too wide. I don't really like it when data is too wide or too narrow. I kind of want it to be around the same width. So for that, I do the standard deviation. The standard deviation, when the data is centered, is the average of the squares and then take the square root. So square root of 14. So what I do is I simply divide by the standard deviation. So I divide every one of these 3 numbers by square root of 14. And I get something that has around width 1 and centered at 0. That's how I want all my data sets. So you should do this for every data set. You center it and then you scale it. Center it by subtracting the average, scale it by dividing by the standard deviation, and that's called normalized data. So when you have data with average 0 and standard deviation 1, you have normalized data. So let's get back. So now we're going to normalize these green and red scores. These scores are called ATI, where T is the solution, 1, 2, 3, and I is the step. So step 1, step 2, step 3 for the answer. So this is how they're called, A11, A12, etc. When we take the average, it's 0.111, the average of all the numbers here. And then when you take with standard deviation, we get 0.578. So if I subtract the average and divide by the standard deviation, then we get this ATI hat, and the numbers are over here. They didn't change so much, but we know that they're centered and that they have standard deviation 1, which is a good thing. So that takes care of that A, which is the quality. It's also called the advantage, and sometimes today I'll call it the advantage. Now let's get to the next one, which is the probability of the responses. This is this pi theta over pi theta all that you see over here. Now, if you're liking this video, please hit subscribe and you'll get to see a lot more material that I'm putting out, and hit that bell so that you can get notifications. So the idea is the following. We have the same problem as before. Solve x in the equation 2x plus 4 equals 10. The solutions are going to be slightly different. We're going to have the original solution, the before solution, which is the bad one. Everything here is bad. The steps are bad and the answer is bad. And the idea is that the model is going to do one iteration and then come up with a new solution. And this one's actually pretty good. Now, this is overly optimistic. The model's not going to go from really bad to really good in one iteration. But what we want to do is we want to grade the model on how much it improved. Or if it got worse, we're going to tell it that it got worse. And for that, we're going to use probabilities, because these models don't just return things. They actually return probabilities. So for example, when the model said the answer is x equals 2, what happens is that it provided a bunch of probabilities for possible answers. Let's say for simplicity that the possible answers are 2, 3, and 4 for x. And the model said, you know what? The probability for 2 is 60%. That's the highest. And then from sampling, it outputted a 2. It could have output a 3 or 4. But I hope you agree with me that it's more information to get the probabilities than to get the actual solution. And we would want a model that outputs 3 with a higher probability. So this model over here said, well, the probability of the answer being 3 is 0.7 and the others are smaller. So clearly it improved, because it went from 30% of probability to get 3, the right answer, to a 70% probability. And also, the wrong ones went from 6 to 2 and from 1 to 1. So there wasn't an improvement on the third one, but there was an improvement on the first 2. And so we're going to tell the model that it did well in the first 2 and that it didn't do much for the third one, but it's okay. It didn't mess up at least. So we're going to have something called the old policy, and that's called pi sub theta sub old. Why such horrible notation? I don't know. Well, pi I think is for probability, because probability starts with p. I don't know why they didn't say p, but anyway, pi sub theta. Theta is the parameters of the model, so it's just a big vector with all the parameters. And old means the old one, and the other one, the new one, is called pi sub theta, so that's the one after one iteration of the model. And as you can see, the numbers changed, and we're going to calculate that changing policy by dividing the new policy divided by the old policy. So this can tell us if the policy made the probability bigger or smaller or kept it the same by just looking at this ratio over here. So let's look at what the changes in policy are. For x equals 2, it went from 0.6 to 0.2. So the ratio is 0.2 over 0.6, which is 1/3 or 0.33333. For the next one is 0.7 divided by 0.3. So it's 2.333. And for the last one is 0.1 divided by 0.1, which is 1. Notice that this is a good step because the probability of the correct answer went from 0.3 to 0.7. So we want the model to do more of this, and we want to tell it you did really well. Keep going in that direction. So in other words, we want to tell it for the first number, continue making it smaller. I want this 0.333 to be really small because I want to decrease the probability of the solution x equals 2. That's an incorrect solution. For this one over here, the correct answer, I want this number to be even bigger. I want it to increase the probability of the answer being x equals 3. And this number over here, I want to say, hey, 1 is not enough. I wanted to make this number even smaller because I wanted to decrease the probability of x equals 4. So basically, we want to multiply this number by something positive and these two by something negative. And I wonder if there's a number that can help us here. Well, we can go back to the advantage or the quality of the response, because we had some numbers here. Remember those A hats? They were +1 for this one, +1 for this one, and -1 for this one. And so all we have to do is multiply the advantage by the ratio of probabilities. And then we get something like this. Negative number for the first and the third, because we want those to decrease, and a positive number for the good one, for the second one. Recall that these are for the solutions x equals 2, x equals 3, and x equals 4. And the idea is that we want the model to do more of this, and that's why we give it a positive score for the good one, a high positive score if it's reducing the probability fast, and negative scores for the other two. So now we figured out this part of the probability, and notice that it used this quality of the response. Now notice one thing is that this summation is given over all the steps. I showed you how to calculate the ratio of probabilities times the advantage only for the final step, which is the solution, but this is done for every single step. So if you have a random step and it's changed to another step, you still look at the probabilities of that step being outputted and do the ratio. Notice that it appears again here, but it's still the same one. The reason it appears twice is because of this clip function, which is what we learn next. We're going to learn how to clip the response. This is a pretty common step that gets used a lot in training, especially LLMs. And the idea is that we don't want numbers in this formula to be too big or too small. If we have 1,000 there, it messes everything up. So we want things to give information, but not be too big or too small. And here, there's not a risk for things being too big or too small, except for this part over here with the ratio. The moment you have a ratio with probabilities, things can go berserk, because if I have something divided by a really small probability, this number could potentially blow up. So we have this clip here to make sure things don't get too small or too big. And it works like this. Let's say we have two policies, the old one and the new one, and the probabilities are not so different. For the two possible solutions, probabilities are 0.999 and 0.001, and the next one is 0.9 and 0.1. So they didn't change that much, but look at what happened with the ratio. The ratio new policy over old policy. For the first one is 0.9 divided by 0.999, which is around 0.901. So that's a manageable number. But look at what happens with the next one. That didn't change so much, but the ratio is 0.1 divided by 0.001. That's 100. 100 is a big number to put in a loss function. It can mess up your model. So we don't want this. This is too big. So let's say we want to make it at most 5. So how do we make it a 5? Well, use a clip function. Clip function says, if your number is too big, let's say bigger than 5, make it 5. If it's too small, like it's smaller than -5, make it -5. And for all the other ones, leave them as is. So it keeps everything here in between as is. Everything that's too big turns it into 5, and too small turns it into -5. That's why it's called clip, because it clips the ends. Now, 5 and -5 are still too big. What we want to do is pick a small number epsilon. For example, epsilon equals 0.2. And then say if you're bigger than 1 plus epsilon, you're 1 plus epsilon. If you're smaller than 1 minus epsilon, turn it to 1 minus epsilon. Otherwise, everything between stays the same. So I like to imagine it like this. You have the number 1 here, and you have a bunch of points. Some of them are too big and some of them are too small. And then you say at 1.2, which is 1 plus epsilon, I'm going to put a line. And at 0.8, which is 1 minus 0.2, I'm going to put another line. And everything that's between the two lines stays as is. And everything that is above the top line or below the bottom line goes to the line. And then I almost have the same data, but the numbers that are too big or too small kind of stay closer to where I want it to be. And that is the clip part. Now we need one final step, which is making sure the model doesn't change too much, and that's this one over here. Notice that it has something DKL, that's the KL divergence. And that's just a way to compare distributions. So let's say that your original policy gave you this answer. The possible answers for the problem are x equals 1, 2, 3, and 4, and the probabilities are 0.1, 0.1, 0.4, and 0.4, and let's say that the correct answer is 3, x equals 3. So we want the next iteration to improve the probability of x equals 3 to make it bigger and to decrease all the other 3 probabilities. Now, after an iteration of the model produces 2 new outputs. And you're going to help me out. You're going to tell me which one you like more. So the first one is candidate 1, which turned the solution x equals 3 from probability 0.4 all the way to 0.5. So it increased the probability of the output being x equals 3, which is the correct solution. And candidate number 2 is this one over here, which increased the probability of the output being x equals 3 from 0.4 all the way to 0.55. So this one looks better because check it out. It increased the probability of the output being x equals 3 more than candidate 1. So which one do you like more? Well, I hope the suspiciousness in my voice hinted that maybe given the trophy to candidate 2, is not exactly what we want. Because compare candidate 1 and candidate 2 to the original policy. Notice that candidate 1 is very similar to the original policy. It almost has the same probabilities, 0.1, 0.1, and it changed this one a little bit, and it changed this one a little bit, but it's almost the same. It's a small change from the original. On the other hand, candidate 2 is widely different. It changed the numbers a lot. For example, it changed the probability of x equals 1 as the output from 0.1 to 0.35. And it reduced the fourth one from 0.4 to 0.05. So it really, really changed the model. And that's not good. We actually want to give the trophy to candidate 1 because it improved and it didn't change too much. It's like, imagine if you wrote a test and the professor says, okay, you did pretty well except for these 3 answers over here. You can do 2 things. You can change those 3 answers a little bit, or you can change all of them widely. And maybe changing all of them widely gave you better answers for those 3 wrong questions. But the fact that you changed it widely makes it pretty risky because maybe you had some correct solutions and made them wrong. So in other words, we want the model to change very little. And for that, we are going to use something called KL divergence, because if we grade these 2, well, maybe this one's going to get a better score. We need to subtract something to the score, and we're going to subtract is the KL divergence. We're going to subtract it and multiply by some coefficient beta. This is a hyperparameter that we can choose to train our model better. And so that's it. That's GRPO. The idea is that you use this function to train your model. So thank you very much for your attention. If you like this video, please subscribe to my channel, serrano.academy, for more material like this. If you want to support me even more, you can join the channel or support me on Patreon. You'll get some really cool perks like early access to videos or Q&As with me, or your name on the videos. My videos will always be free, but if you subscribe or join, then you can get all these cool perks. You can also follow me on Twitter, Serrano Academy, or check out my page where I have a lot more information, including papers, labs, blog posts, and all the videos. And also I have a book called Grokking Machine Learning, which I highly recommend you to take a look. It explains supervised learning in a really fun and friendly way. Here is a discount code, SerranoYT, that gives you 40% discount. And for that, you can look at the link in the comments. So thank you very much for your attention and see you in the next video.